Right. Good afternoon, everybody. I'll do my best to stick on time. It's a sharp session. I'm going to start by taking 2 points, one from Professor Miles and one from the lady from MSF. First of all, we're living in a time where we have a lot of hype. My background is on RNA interference, and it was supposed to cure all these undruggable targets. We know where that went. We have the lady from MSF telling us about all these fantastic new technologies, but what do they do in the field? So that's the approach I take to the work I do. Try not to do hype, try not to do things that are not practical. So I'm going to talk to you today about a group project that I'm leading called EbolaCheck, which aims to deliver basically at-cost humanitarian crisis rapid diagnostics for where it's necessary, for where it can answer the problem at the point of need. So I'll briefly touch on the topics of how do we deal with high containment agents and what does that mean when you try to get into West Africa, which is what we were trying to address. What is the EbolaCheck concept? How do you use it? And it's a shame the lady from the MSF went, but we've got colleagues from Africa here who might be able to tell me if this is too complicated. I have pushed very hard. The technical advances we have done and where we are in terms of prototype development. So when it comes to Ebola, the standard of care, there are various ways you can do this, but the truth is the standard of care is detecting the viral genome by RT-qPCR. So it's a negative RNA genome, you need the RT step. You need to take 3.5 mils of venous blood, about a teaspoon, transfer it to a molecular diagnostics lab, extract RNA, make it into DNA, quantify the viral genome if you can, and get the results back to the patient in the best of circumstances, somewhere between 5 to 8 hours. Now, of course, Ebola is highly infectious. You've got to stick a needle into a person, one of these two types, hopefully the sheathed one, use a vacutainer to collect the blood sample, and then take it to an environment that looks something like this. Basically a containment hood, people in full PPE trying to operate in a very clean environment very safely. Now, this is what West Africa looks like, okay? We've got people living in really tight environments with very little sanitation, and I don't think we're talking about very high access to healthcare. There are others that are experts in this that have covered the topic over the last few months. If you go to the rural settings, in the most remote of villages, you're in the jungle, you don't have electricity, you don't have running water, and if you go into towns where you have motors of sorts, you still don't have any power lines. That's a tree, by the way. If you go into the primary healthcare environment, you've got definitely Windows, none of the Microsoft Windows on software or anything like that, let alone electricity. This is where people get treated for pregnancy, for Ebola, you name it. Okay, so this is the kind of environment that we have to work with and offer to the patient a solution. And we need to get it there, and this is what a transport route looks like. This is a main highway, by the way, leading from the capital of Sierra Leone, what would normally be in England an hour away to a rural area. So if you're in the urban environment, you could probably quickly get to a diagnostic center, but that won't have the necessary capacity, and I doubt you will have the money in your pocket to pay those guys to analyze your blood sample. If you live in the rural environment, you either transport the patient somehow, or you walk, if you can, to the care center. The truth is, especially at the height of the Ebola outbreak, most people were being diagnosed post-mortem on whether or not they had the infection. So there's clearly an acute need for a point-of-care molecular diagnostic solution. Ebola made it come home to most people in the Western world in the last 6 months. I hadn't seen the assured principle list when I first wrote this slide deck. So this was my version of it. It doesn't read very well as an acronym, but it says safe, cheap, simple, robust, portable, battery-operated, all the stuff you see in the assured principle list. And this is the concept. On the right, this is the EbolaCheck instrument. As you can see, it's fairly large, and the reason why it's just a little bit over the A4 size is because we were asked by our colleagues from Public Health England not to make it small, not to make it portable, because things were being stolen from the treatment centers at the beginning of their response efforts. So we make it actually purposefully big, but we have a version that's handheld. It's got a nice touchpad screen, so you can prod at it with a big fat glove. It's got big consumables you can hold in your hand very easily. 8 independently operating power stations. It runs on a car battery or a solar panel. All the reagents here are freeze-dried, so it's cold chain free. It's ruggedized. It gives you a negative result in under 40 minutes and a high positive in under 20. It's simple to use. We'll see what that means. And it's reliable. It has a detection target of less than 10 to the 4 viral genomes per mil. And we achieve that by putting in it the standard of care molecular diagnostic assays. Now, a lot of people have been throwing numbers around, and I got permission from my company collaborators to put finally a number onto the slide deck. The cost of goods, the cost per patient, is less than $12. So if you talk to the experts of developing diagnostics, they'll tell you a system is composed of many subsystems. So in this particular case, the EbolaCheck system has the instrument, the assay, the master mix, and the consumable. And the system relies on a single tube process, which is direct extraction, reverse transcription, and qPCR in one little vessel. There are no microfluidics, which explains why we don't have that high costs. It has a high efficiency rapid thermal cycler and a heated optical sensor lid. The master mix is proprietary. It's the one thing I won't be able to share any information on today. It is, however, whole blood compatible and lyophilized. And the assays detect the glycoprotein and the nucleoprotein of the Ebola virus genome. And we use a human RNase P endogenous control. These assays were developed by United States Army Medical Research Institute for Infectious Diseases, those that followed the Ebola outbreak. The first assay that received FDA emergency use authorization was from these guys. I think it's this particular assay. The RP assay is a CDC assay that's been used for years. So we use very well-validated assays in the system. Our performance targets 7 logs of dynamic range, a lower limit of quantification of 30 copies of genome, a lower limit of detection of under 10 copies. Now, my industrial collaborators were a bit upset when I put those down on paper, and they were like, Sterghios, this is aggressive. I was like, yes, I like aggressive. So, use protocol. Step 1, take the little tinfoil thing off. It comes with an easy peeler. Step 2, rehydrate the consumable in the coffee dispenser-like machine that we provide. Then you use the microsafe capillaries we saw in earlier slides today to collect a drop of blood, in this case 10 microliters. You then put that 10 microliters into the consumable, put the lid, again that's got an easy handle as well that snaps off very easily. Put it on the machine, lower the head, and then go to the touch screen. You press the station that is of interest to you, for example, station 2, that becomes active. You put the patient ID, MSF, PHE, whichever system you'd like to use, your username, so that we can tell if you can do the assay properly, and press the start button. Simple. It took 3 months of arguing with engineers to get it this simple, believe you me. Come on, Sterghios, we can use a pipette. No, you can't. You're wearing full PPE at 45 degrees. Anyway, if you're lucky enough, the instrument will return this, no virus, universally understood negative. Or this, hopefully not, virus detected, or definitely, hopefully not, there's a problem, please repeat the assay. That's all the information shared to the frontline healthcare worker. So how did we get to be able to work with this, not working at Port and Down or USAMRID or something like that? We took the armored RNA quant product from Assuragen. This is a 26 nanometer phage. It's available off the shelf. The design that we've put in it is available off the shelf if you wish to buy it and you don't want to talk to us. And we also took pseudotyped HIV, which is a technology my colleague at Westminster, Ed Wright, is an expert in. This is an 80 to 100 nanometer HIV construct with a lipid envelope, much like Ebola. However, it is quite different in that Ebola is a string. It's 18 nanometers by 14 microns. We've got isolates, etc., genetic drift. However, we have some fairly good internal diagnostic standards to play with and get some performance numbers with. We've also done a lot of characterization of the preps to be able to say we know what's in those preps and they're actually high quality. So quite excitedly, with this technology in the hands, we started trying to do direct whole blood RT-qPCR, and we had a problem. This are actual data when you see from 0.5% blood in your reaction to 1%. So I think I would build a house on this one because it's that flat when you go further up. The problem is you lose efficiency in the reaction and fluorogenic signal goes down. So at this point in time, even though we had reason to believe previously that we shouldn't have a problem, there are a lot of people out there that say they can put out PCR enzymes and technologies that do this in the whole blood. Clearly there were problems. We thought for a moment maybe we can play with intercalating dyes instead. That didn't really affect the problem. We still have loss of fluorogenic signal, and we also have loss of efficiency. The problem we encountered now was too much high background because of the DNA in blood. So to try and reconfigure the whole technology, we developed this single well instrument. These are just for demonstration purposes only, but this is the business end of the machine connected to the tablet. And we started playing around, and lo and behold, I'm sorry I can't tell you what the formulation is. We have taken now the standard Trombley assay for Ebola diagnosis. We've changed certain elements on the way the light is produced. We've changed certain elements in the master mix. For example, excipient A, increasing concentrations, that's a nice amplification curve. So just to make it clear for those of you who haven't seen an RT-PCR before, this is the number of cycles we're doing. The sooner you can get this to climb up, this amount of fluorogenic signal, the better. As you can see, we've restored it all up, back to where it should be. We then tried to see whether or not this performs equally as well as the Trombley assay if you put it into the standard clinical instrument, the ABI 7500. These are triplicate curves, right? This is how good Kavit Shah is, who's the guy who does all this work. You can see here we have an increase of about 3 cycles, which translates to an 8 times increase in sensitivity by changing the chemistry. So these are just the primer probe system shifted to the Trombley Plus on RNA extracts on the standard clinical instrument. Next, we looked at dynamic range and low limit of sensitivity. 9 points, fairly straight, 0.99 on the R squared. We're going down from 1 to 9 log copies of the viral genome. This is the CT number, the cycle number that we saw in the previous graph. So as you can see, it's nice log linear relationship for the 2 assays. Incidentally, this is 2 logs higher than our 7 log target, so we're quite happy with that. And then we put the assay on both systems, the ABI 7500, and we put it also on the QRapid. And lo and behold, we get nice amplification curves for both. Please note, you cannot directly compare the threshold cycles here between the 2 instruments. The volumes are different. There's a lot of thermal modeling that's different. This is just, we can do it, okay, on the instrument. Does it work in blood? Well, let's go to that. Here's the data of the qPCR product, QRT-PCR product. If we increase the extraction intensity, too much of some things is too bad. You can kill your template, but an extraction intensity of 10 arbitrary units, you can get the amplicon that you want. This is actually on a manual method that took about 4 hours for Kavit to complete. Not very precise, but it proves the principle that we can get the amplicon where we want it. 33 copies, not bad. So let's look at it when we're playing with the QRapid. So here's again your extraction intensity axis. Remember that magic number of 10 extraction intensity units. Here's your threshold cycle. The lower the number, the better. You can see we've got agreement with the automated system that took how much, Kavit? 2 minutes? Something like that. So a lot faster, a lot better. Clearly the optimal range for armored RNA is around 8 to 10 intensity. And that basically is for a phage, which is a really tough particle. These things are, tough as nails. Let's look at what the effect of blood is onto the instrument. So now we start with 0% blood. We start increasing the concentration of blood, and as you see, the threshold cycle drops. But because we have our formulation modifiers that we know will work at a better concentration of blood, we see this curve coming back down again. It looks like, as we're going to be progressing through these experiments, literally this was developed last week, we should be able to go back to optimal performance or as close as to optimal performance. If you do the math, this means we could detect 1 viral genome per mil. Not bad, I think. Sorry, that means, viral genome per microliter. Sorry for that, or CT34. You can go and look at the EZ1 FDA approval documentation. It's in the same range. So what have we achieved so far? We've developed high-quality biosafety level 2 standard safe. They're off the shelf or open access, whichever model you prefer. The National Institute for Biological Standards and Controls have actually adopted our methodology and our validation approach. So the international reference standard being developed right now is using ED's principles on this. We have transferred 2 assays successfully on the QRapid instrument, made them 8 times more sensitive and shown 9 logs of dynamic range, and got them onto the QRapid. We have duplexed with the RP control. I can show you that data if you want. And we have proof of principle. We can triplex the 3 assays in the same vessel as a minimum. We have resolved the fluorogenic inhibition in blood and also the other problems, make it work on the QRapid, and we've shown we can lyophilize. We've got a testing rig for any changes that may be needed later, but we doubt there's going to be anything. We've optimized the extraction power, and we've got 10 instruments in production. But we have the proof of principle in blood that we can detect a viral RNA with our methodology. In the next month, we will optimize the master mix, get the performance metrics for you, and perform some blinded testing. And after that, it's off to PHE and USAMRIID, where they will reconfirm their own assay's analytical specificity. They will also do blind testing in guinea pig and NHP models of infection versus the clinical diagnostic approach. Thankfully, there's not that many new cases of Ebola in West Africa, so the chances of us testing it in patients are very low right now. However, the UK Ministry of Defence have agreed if there is a resurgence, they will test the system for us. We just got an agreement yesterday completed with the EM lab to actually give us access to stored plasma samples to do also testing, but that will require some equivalence testing with the effect of EDTA, etc., on the reaction. And after that, we will transfer 3 instruments to the Kwame Nkrumah University of Science and Technology in Kumasi, Ghana, and they will take them out with mock samples with armored RNA to the jungle, to the seafront, to cities, to dust places, and try and repeat the results. They will not know how much, if there are any armored RNA particles in the tubes. They will just send us back the data in a blinded fashion, and we will decode it by a third party, just as if it was a clinical trial, to see if it does what it says on the tin. By autumn, we will have optimized the duplex and triplex assays, and we will also explore mucosal biofluid utility. Somebody mentioned earlier people don't like getting pricked with needles. I don't like needles. I really don't like needles. Turns out your crevicular fluid is a very good depot, so that's the fluid between your tooth and your gum, for viruses. So we're looking into those kind of biomaterials. We also know that breast milk, semen, tears contain Ebola in people that have recovered from the disease, so it's worthwhile exploring these matrices. We'll work to minimize the reaction times as much as possible, study whether a white ethnicity, black ethnicity, Asian affects the results, and then move to transfer 6 additional HFD assays onto EbolaCheck. And the goal here is that through all this work, we will explore the potential to develop a differential HFD diagnosis panel between 12 and 15 assays strong in a single vessel with an increase in cost of goods of less than $2. This is not just me throwing numbers around, guys. We've done the mathematics on this. The point here is I'm not making any money out of it. Neither is the company who's manufacturing this instrument. This consumables and the instrument are available at cost for this Ebola crisis, and we are negotiating with the funding bodies right now for them to accept for any WHO-declared humanitarian crisis. So if tomorrow there's another virus from some other bat that causes a problem, just get the right primer probe set validated, we put it in the machine, off you go. No profit. That doesn't mean that there aren't profitable applications, because you're never going to get a company interested in this. There's all sorts of things, molecular medicine, agri-food, biodefense, you name it, where people can pay for. And I really like individuals like Donald Trump shouting, lock patients, lock people away from United States. We don't want to get infected with Ebola. Mr. Trump, here's something you can put in the airport and pay for it if you like. You'll pay through the teeth. But, the people in Africa will not suffer. So I'll close here, and I'll thank the long list of collaborators I have on this. We started this work in August as a sketch on a piece of paper. We got the money in November. We now have 3 instruments nearly completed. We will have 10 instruments by the end of the summer. I had somebody say it takes 2.5 years to make an instrument. I challenge you, don't wait for the next Ebola epidemic. Look at those barriers, think how you can go around them. Going over them is too difficult, okay? find the solution, get out there, get to people that want to do work, and get the work done. Thank you very much for your attention. And by the way, Sierra Leone is a very beautiful place. Cameron, can we go there next year, please?
Yeah, I'd love to.
Thank you.
Yeah.